Hello students, today we'll be seeing about quantization noise. In this video, I'll be explaining about definition of quantization, types of quantization, what is quantization noise, and finally we'll be deriving expression for quantization noise and signal to noise ratio. So what is quantization? Quantization is nothing but in the process of converting an analog signal into its digital form, we need different levels which we call as quantization levels. For each and every level of quantization, a discrete value will be found from the continuous analog signal. Say a continuous analog signal like voice signal will be having continuous set of values. These continuous set of values will be discretized, so that for each and every quantization level we will be having a discrete value. This is called as quantization. It is nothing but representing the sample value of the amplitude by a finite set of levels. So as shown in the figure, quantization is done for the analog signal here. So for every increase or decrease in the continuous range of values which we call as analog signal, the step size of the quantizer will increase or decrease respectively. So for each and every value of the x-axis, which is a timeline, we'll get a discrete output value. So this is called as quantization, and this figure actually shows how an analog signal gets quantized. As you can see, for each and every point of time in the x-axis, you get a discrete y-axis, which is the digitized value of the analog signal. So this is the figure which shows the resultant quantized signal alone, which is somewhat like digital form, because for each and every set of input we have a discrete output. There are two types of quantization. One is uniform quantization and another one is non-uniform quantization. When the step size of the signal is uniform, when it is fixed, then we call it as a uniform quantization method. If the step size varies with respect to the change in the continuous signal, which is the analog signal, then it is called as non-uniform quantization. Here uniform quantization is divided into two other types, which is called as mid-rise type and the mid-thread type. So there are two types of uniform quantization, as I said before. One is mid-rise type, another one is mid-thread type. Mid-rise type is nothing but here the origin lies in the middle of the rising part, whereas in mid-thread type the origin lies in the middle of the thread of the staircase like graph. So this is a small difference between mid-rise type and mid-thread type as shown here in the figure. So this is all about quantization. Now let's see what is quantization noise. When you quantize the continuous form of signal, there occurs some error between the quantized signal and the original signal, which is called as quantization noise. When you quantize at each and every time interval at different quantization levels, that at that point of time the difference between the original signal, which is a continuous signal in that timeline, and the corresponding quantized signal gives you the quantization noise. It is either called as quantization error or quantization noise. So in this example we can clearly see that the blue line is the continuous analog signal, which we call as true signal, and this green line is the quantized signal, and the red line shows the quantization error. This error, which is obtained during the process of quantization, can be represented as epsilon, which is given by hq of nts minus h of nts, which is the difference between the quantized signal and the original signal at the time ts. Now let's say that the total amplitude range is from positive h max to negative h max. So the total amplitude will be 2 h max. So h max is the maximum amplitude level. With that h max we can derive equation for del. When the entire range of amplitude of the signal is quantized with q level of quantizer, then 2 h max by q will give you the step size of the quantizer. We're going to split the signal, the entire range of amplitude of the signal into q levels of quantization. So that will give you the step size of the quantizer. When you consider h max to be 1, then the del value becomes 2 by q, wholly depending on the quantization level. When the quantization level is huge, or when the quantization level is high, it means that the step size will be very small. In that case, when the step size del is small, the error that occurs because of the quantization process can be considered as a uniformly distributed variable within the range minus del by 2 to del by 2. So here we are considering mid-rise type of quantizer. So it ranges from minus del by 2 to del by 2. So before going deep into that, let's derive equation for this step size del by considering the value of q. So q, as I said before, is the quantization level. Any number of levels can be derived from the number of bits per level. So here we are considering v as number of bits per level. So q can be derived from the equation 2 power v, where 2 power v gives you the number of quantization level. If let's say that if the number of bits per level is 4, then the number of quantization level will be 16. So on substituting this value of q, you get the step size del as 2h max by 2 power v. So we'll be using this del value to be substituted in the equation of noise power. So let's keep it as such. Now let's come back to the factor that if we assume del to be very small, that is there are more number of quantization level for that particular range of continuous values, then the del size will be small. If the del is small, then we can assume the quantization error as uniformly distributed within the interval minus del by 2 to del by 2. When you consider epsilon as a uniformly distributed random variable, then we can express the probability density function of that error as f epsilon of epsilon, and this f epsilon of epsilon will have value 1 by del from the range minus del by 2 to del by 2 and 0 otherwise. That is shown in the figure here, which is the uniform distribution of the quantization error. Here the noise power is given by v square noise by r. Normally the power equation we know that v square by r. So here the noise power we are taking the same equation, and we are also going to consider for simplicity the value of r to be 1. So our aim is to find the noise power, which is nothing but v square noise. Here we have to square the voltage values. Since we are considering epsilon as the probability density function, the mean square value of the probability density function f epsilon of epsilon can be written as integral minus del by 2 to del by 2 epsilon square f epsilon of epsilon d epsilon. So we know the value of f epsilon of epsilon over the range minus del by 2 to del by 2, which is 1 by del. So now we are going to substitute this value and integrate it. Here we have substituted the equation for f epsilon of epsilon, and when you integrate it, the value of 1 by del, which is the constant, can be taken out, and epsilon square alone will be integrated, which is epsilon power 3 by 3, and on substituting the limits, you will be getting del square by 12. As I said before, the value of r will be considered as 1, so the obtained quantization noise power is del square by 12, which is one of the important derivation which will be used in problems. So we have to remember this. The noise power which we obtained is del square by 12. So this is the step-by-step procedure which I have written how del square by 12 is obtained. So initially, as I said, 1 by del can be taken out, then on integrating epsilon square we get epsilon power 3 by 3. On substituting the upper limit and the lower limit and subtracting them, we get del square by 12. So now we have obtained the equation for noise power, which is del square by 12. Now it's time to apply it in the signal to noise ratio to obtain equation for signal to noise ratio. Signal to noise ratio is nothing but the ratio of normalized signal power to the normalized noise power. So we already know that the normalized noise power is del square by 12, and we also know we have also derived equation for del, which is 2h max by 2 power v, where h max is the maximum amplitude of the signal and v is the number of bits per level. So we are going to substitute this in the value of signal to noise ratio. When you substitute this and when you assume the normalized signal power as P, you will get equation for signal to noise ratio as 3P into 2 power 2V by h square maths. So this is the equation for signal to noise ratio. This is the step-by-step procedure for obtaining the signal to noise ratio for better understanding. By viewing the signal to noise ratio, which is 3p by h square maths into 2 power 2v, we can say that the value of signal to noise ratio increases exponentially with respect to the value of v. V is nothing but the number of bits per level. As the number of bits per level increases, the signal to noise ratio increases. So when compared to other methods like frequency modulation or pulse position modulation, the use of binary code for message signal actually produces good signal to noise ratio. But the only drawback here is the bandwidth requirement. As the number of bits per level increase, the bandwidth requirement will also increase. That is the only trade-off. Other than that, this method seems to be producing good signal to noise ratio. So initially, for deriving expression for signal to noise ratio, we derived expression for the step size. Then we substituted that step size in noise power to derive equation for noise power, and finally we calculated signal to noise ratio by assuming the signal power to be P. Hope you all understood. Thank you.